Hello, everyone. Good morning. Welcome back. We are in week 6 of the program. And like I mentioned last time, this week and the next week, we'll be really going deep into the core topic of this year's program. How do we solve differential equations on quantum computers? And the topic for today is particularly about nonlinear differential equations. A few weeks ago, we had Andrew Childs, Hari Crowe, and Herman Kolden on the program, and they talked about how one of the key challenges in solving differential equations is how we efficiently handle nonlinearity. This because any real-world application, real-world PDE or ODE that you take in, it's going to have nonlinearity. So, efficiently tackling nonlinearity becomes a key challenge if you want to develop better and better quantum algorithms. So for this, we have Dr. Pedro Costa from VQP. I'm very excited to welcome him to the program. Pedro is a quantum computing researcher with a background in physics and expertise in both classical and quantum algorithms. His research spans Hamiltonian simulation, differential equations, optimization, and he has contributions to both the classical and quantum approaches to complex computational problems. And he has the best known results for the quantum linear system problem. He has collaborated extensively with top research institutes like at Google and Microsoft, and also top academia institutions such as with the Macquarie University, UTS, and the NSW government. And now he's at BQP. He focuses on developing efficient algorithms to advance quantum technologies and their real-world applications. And I'm very excited to welcome him to the program. And over to you, Pedro. Thank you for being a part of it.
Hello, thank you for the introduction. Thanks for having me here. I'm excited to talk a little bit about these algorithms and see if I can share a bit of these challenges and knowledge that with the folks here. Okay, so the idea here is to prepare more like a lecture rather than just a sequence of slides that sometimes can be, I think, too fast or maybe a bit boring to the folks follow. So my goal here is to see if I can step by step derive some of the ideas of the linearization, and then you get familiar when you see this kind of problem or you see some of the papers results that are gonna, when you face this kind of problems, it's gonna be natural for you to see what you are dealing with. So, and then what is the challenges of the deal with nonlinear difference equations for quantum algorithms actually in general, right? And so what I try to do here, I'm gonna focus in 3 parts of this presentation. I hope I have time for that. But my hope is that you can leave this lecture here today with some basic and important concepts about how the linearization works in the different cases. Actually, I would like that you understand at least 2 different cases. Like in the first part that I would like to talk about when I have to deal is like a toy problem that people have to deal with. So just to introduce the linearization in terms of Carleman approach, which is the case that we have a scalar nonlinear ordinary differential equation. Then I'm gonna move for next step for the vectorial case. So I have now a system of ODEs, the nonlinear ODEs, and I'm gonna show how to step by step how to linearize this. And then I'm gonna move for the Carleman arrow. So this is really crucial to see if you can have something efficient, if you can deal in the quantum algorithms. And then I can talk a little bit about the stability of the problem, the dissipation, and how that is used to guarantee that you have an efficient algorithm. And then I'm going to talk really one of the important improvements that have done in our previous works about rescaling of the nonlinear ODE, which is give you at the end exponential improvement compared with the previous results, the exponential improvement number of quantum queries that you needed in that approach. And then if I had luck, I'm going to show how we're going to move for the nonlinear differential equation. So then we're going to be the example case of the PDE, nonlinear PDE. And then I'm going to show how we can map this particular case to the nonlinear ODE. And then you can continue from there, like and then doing the linearization and then apply ODE solvers from that. And I believe here that I have a previous presentation that like Dongan, I think, that show how to deal with ODE, general ODE cases in the quantum computing, in the quantum computer. So here I can try to mention a little bit how that works. And for example, have some subroutines like you can use like linear system solvers for that. But I'm gonna just try to be quick on that part because I don't have much time. And then in this third part, I'm gonna show why, based on this Carlemanization based on finite difference methods that normally people have to deal with. So you also have a case with the Boltzmann-Latze, which is a different approach to deal with the discretization for the nonlinear cases. But in the case that you have to deal with a finite difference method, I'm going to show why that Navier-Stokes type of equations you cannot handle in the quantum algorithms the types of equations like Navier-Stokes. Okay, so let's start. I'm gonna go like as I said, like step by step, showing how with the problem that we have and how the linearization works. So yeah, suppose you are dealing with this following scalar ODE, nonlinear ODE. So in general, you have, suppose we have here the following difference equation. So we have this function fx, and you have x is just a scalar number here, okay? That depends on t. So I should be actually, just to clarify, that's time dependent here. Okay, and then you have of course, some initial condition that you can call it by x0 here. So now imagine this function fx is give you some nonlinearity in x, some polynomial, right? So suppose you are dealing with this kind of problem here. So a polynomial of order n here. So again, some coefficients, scalar, that is not important now. So the main idea of this Carlemanization is that you have to define new variables, right? You have new variables that are going to be related with these nonlinearities. So the main idea is to define new variables. Okay, and here we're gonna call by y. That's usually people does. Right? Okay, that's the start point here to make the nonlinear turn that in linear. So then we're gonna just apply some chain rule of derivatives, so everyone knows how to do that. So you do that. But you know what is x, so that's gonna be just the derivative x minus 1, and then we're gonna have dx dt. And then dx dt, you know that from the original problem that you have, like, so you have the equation 1, you know what is the dx dt. And the dx dt is just fx. So we're gonna just put all these things together. Right? So then I have the equation 4. And actually this, we can now just a step further. This is gonna be j. We're gonna just use the polynomial that you have, define it. I hope you can understand my letter, because my letter is already not good that good, and then in the iPad make it worse. So okay, so then I can go back to the definition of the new variables that I did. So everything is in terms of x, then I go back to in terms of y's. So this is going to imply that in terms of y's, you have this linear combination of new variables y's. So then we start to couple the system in terms of y's, which everything is now linear in y. But in terms of new variables. So I hope that's the main results here that I have to concentrate. So what that means here that we're coupled the system, right? For example, so then if I just rewrite this for y equal 1, for example, okay, I just replace j for y for 1, and I can continue doing that. So you see that every term, new term is now coupled with the other terms. And then if I move for dy2, I'm going to continue with that. The factor of 2 comes from j. Remember j that I have in the definition, general definition. And then we're going to have ck by k plus 1. And you're going to keep doing that. And that's it. So rather than writing this like one by one, line by line, you can write in the compact way in terms of a matrix. So you can rewrite this in terms of a vector of y's. And then as you also see, that's gonna become infinite, right? So there is no limit for this system of ODEs. So you have to decide when I'm gonna stop, if you have to do that numerically. And once you stop, you're gonna have some errors later. So but just gonna write now, I'm gonna write that in the compact form. And so on. So now you see, remember what C1 is, right? So C1 is coupling with until the end components of Y. So that's gonna have like C1, C2 in each row until Cn. And then if you move for the case with y equal 2, you see that y now is shifted by 1, k plus 1 there. Remember y2 here on the top, as you can see. So everything gonna be shifted by 1 with a factor of 2, right? So they're gonna have 2c1 here, gonna have the continuation here, gonna be c2, c2, and so one gonna have cn, just shifted by 1. And you're gonna continue doing that until cn, like in that case, n minus 1 that I wrote there below, gonna be n minus 1, the factor with c1, and again until cn. And here continue as I said, because it's infinite. Sorry for that. Okay. So here is the compact form of the problem that we just turned something was nonlinear, a general nonlinearity in terms of some polynomial. And then this is just the traditional way to do, like the ordinary way to do the Carlemanization. And the Carlemanization is just one like a special case for example, of the Koopmanization. In the Koopmanization, we can deal with more different type of bases. So here, just dealing with this monomial basis, I can do different types of replacement of a new variable, so you can deal with different types of nonlinearities. But that's not gonna, I will not have time to talk too much about Koopman here, but this is just a special case of Koopman linearization. So then, of course, in practice, you're gonna have to truncate that, otherwise you're not gonna solve anything. So numerically, you need to truncate that. So then here, I'm gonna just consider the truncation of, as people call it, the order n. So then you have the vector y, right? That is has a vector that I wrote. That are gonna have any capital N components. You can leave the smaller n as well here. Yeah. So that's the vector after the truncation. And then if you look at the case, just replace what I did before. In the, for example, the asterisk is here, this equation that I leave here. You can just, if you want to see how going to be the last component, and you capital N, you just go back there. And then I'm going to find out that N However, notice that I don't have more components. So this sum that I have this linear combination of y's is stop already capital N, right? So you don't have more components to go because I truncated. So at the end, you're gonna get it just capital N minus 1, the C N Y N, and what I'm gonna finish with is just make things quicker here. You're gonna end up with the case here, capital N here, and then I just actually I can leave this as it is. And the end you're gonna have just don't have space enough here. The idea that in the end you're gonna have N minus 1, C1, and here we're gonna have capital N. So that's the concept. And then you see that now we can solve one by one, right? We start from the capital N here, the least element, and we're gonna solve one by one until you get the component that you are interested, because at the end of the day, you are interested of the component y1. So y1 has the x, so the solution for x that we're looking for. The other is just the doubling the copies of that. So the powers of that. So then I can also write in a more interesting compact way that you're gonna see a lot in the literature, is that write it is like that. People call this matrix as the matrix A n because it's truncation of order n, and people usually write this. It's a homogeneous equation here, which is clear how you see that is a vector. You are dealing now with you end up with a vectorial case of ODE starting from a scalar ODE, nonlinear ODE, right? So notice that. And then I can apply the methods, traditional whatever method that you want to apply to solve the ODEs. You can like maybe discretize the Euler discretization in time and solve that. Different approaches that you can do. And then I think I need that you pay attention that you see that larger. So notice that larger and better is the precision, right? So you can analyze this. So, but the problem is that larger you have n, larger is the system of ODE that you had to solve. So it's the computational cost, and then also that's gonna have a more computational cost as well in the quantum computation that increase in n. So you always have to find a balance. So because n is gonna give the error related with how much error you're gonna have in the Carleman with the trade-off to have the higher cost. I always have to look at for these trade-offs in the quantum algorithms in general. So okay, so here I think less than 20 minutes. I'm gonna move for the vectorial case, and that's the I think that's the most interesting, and that's what people usually does in the literature. And if you understand that at least this case is already a good takeaway, because this is a kind of people normally you're not gonna see too much derivation about that. People already have assumption that you have already have a good background, or if the introduction is really quick. So that's I think that's the most interesting case to understand.
Hi, Pedro. Sorry to interrupt. Just a couple of quick questions, maybe. So the questions come in through Discord, and I can just ask you the questions. So why n minus 1 is multiplied? In your...
Sorry, what was the question?
Why is there the n minus 1 that's multiplied with C1 in your... If you just scroll up a little bit.
Why minus...
n minus 1. Oh, yeah, here. In the matrix, the right bottom right entry, n minus 1 times C1. Why is the n minus 1 multiplied there? So how?
Oh, n minus 1 here, are you saying?
No, on the right in the matrix.
On the matrix. Here? Are you saying this n minus 1 here?
Yeah.
Okay, so the n minus 1 here. Oh yeah, this actually should be n, should be capital N actually rather than minus 1. Just yes, that's right. That should be n here. That's the question?
Yeah, so I mean, the question was like, how did the term come there? But it just comes from like
this
the
is actually,
right?
There's a mistake here, just n.
Okay. Perfect.
More questions?
Yeah, can you just scroll up to your like the original that you had and like the change of variables, so just people can kind of refer back to the original system and what the yi's are and how they compare. Okay, I think just pause a bit on the slide, and I think there was a question on that. And I guess there's one more question. Are the elements after Cn in the first row of the matrix A 0? And does there exist yn plus 1, yn plus 2 in the Y column matrix?
The question is here?
Yes. I guess the question is I think the question is on like the size of the system. So I think here you have not truncated it, right? So it's infinite.
That's the problem. You don't have a limit in both sides, right? You have the row and the columns, so without limit. So that's, I mean, you cannot deal with that, right, in practice.
Yeah.
Right. So then I mean, you have to come up with some truncation, and then when you have truncation, you're gonna have a clear matrix to solve linear system to solve all of these.
Yeah. Okay. Thank you. Yeah, I think those are the questions. We can keep going.
Okay. Thanks for correcting me on that. Okay. Can I continue here?
Yes, please. Yeah.
Okay. So then I'm gonna move for that case here. So now I have this type of ODE, nonlinear ODE. Again, U is also dependent of time. And then we're gonna have some, so again, UT, you have something like n-dimensional case, right? So it's a different starting point. And then again, UT, T goes 0, you go U 0, just to have some initial condition here. Okay. So then you're gonna see that usually we're gonna have some conditions that, oh, you're gonna write these conditions of like, we have the conditions for R, and then say, oh, R is this the stability that it should certify, but I'm gonna show why the reason for this. So for this case, it's gonna be U in is actually U0, and then we have conditions that the eigenvalues of the matrix F1 is negative to certify that we have a dissipative problem, and then also can explain a little bit why it's important to have a dissipation for these problems. So that's how people usually define. So for example, in the last work that I have derived, we haven't considered F0, for example, so F0, a special case with F0 equals 0. So this term here. So then here start to analyze a few things about this ODE. Well, first notice that here, so this is a Kronecker product. I have to reminder what this is, right? I'm gonna give us just a quick example. Like if you have like just a Kronecker product of 2, right? So gonna be like 2 equal like that. So how you do is like imagine that each of them just for a special case. So there's like example. Each of U vector U has a vector of a 3-dimensional vector, the three components of the element only. And then we're gonna deal with this kind of Kronecker product. So the Kronecker, or maybe the same people call the tensor product, but you here just you're gonna repeat the components here. So you only have U3 into 3 components, and it kind of have this products of each vector itself. So this is actually a vector. So actually going to increase the dimension of the new U2, the Kronecker product. So then we have like U1 square, U1, U2. That's coming from this first component here. U1, U3, and then we have U2, 1, U2 square, and so on, right? So until finalize U3 square. So how that's Kronecker product works. So in that case, you're gonna have in the case you have 2, a Kronecker product of 2. This is the new dimension of that. So you have just the exponential of the dimension that we start with. So in general, so if you are dealing with, that's our problem, which is given by M. this is gonna be element of this new vector n, because n is the initial component that I have for the vector itself, and then gonna be power of n. And then see, you can already understand that the matrix itself, Fm, is not square matrix, the F1, because you are dealing, so you have to deal like at the end of the day, this is a component of any components, and then here you have dealing with the larger, so the vector of the Kronecker product, so you cannot deal with that square matrix. That should be a rectangular matrix. And F1 is gonna be a square matrix, and F0 is just gonna be, in that case, a vector. So that you have already a few information about it, what Fm is. So we're gonna be n times power F1, gonna be element. Could be complex as well, depending on the case that we're dealing. And F0 is just a vector. Okay. Now the derivation is a bit more complication, but how to derive the linearization, but the steps pretty much follow the same. So now how we're gonna do the linearization? Okay. So again, you're gonna define new variables in terms of these monomials, but now we're gonna be in terms of these Kronecker products, right? So that's the new start point. This new definition here. Okay. So then you're gonna just apply this is a kind of product rule or things product rule of derivation in terms of this new variable. So this is have to be more attention here. Remember now I have this Kronecker products. And at the end of the day, I have J components repeating itself, right? And then I apply just as like a sequence of like a product rule here, like in that case, it is in terms of this Kronecker product, you're gonna have then I have again J derivatives of this. Right? And then keep going, and then you finish, like have to do one by one, and that's pretty much what we're gonna end up with. And then we're gonna go back to the previous problem that we're dealing with. So we just go back to the problem that we're dealing in terms of difference equation, nonlinear difference equation, and then we're gonna replace. So then this, for example, the first component is gonna become u power of m so actually it's power of 2. No, I consider n in the original problem, I consider like m, yeah. So it's gonna be power fm plus 1 here plus 0. And this is gonna be a Kronecker product again, the next one, and so on until the end. And then you have to consider that it's being applied for all the cases. Can consider we can for example, if I want just include the last one as well, just hold my time. Well, we understand, right? So the question is that just put one replacement one by one until the end. For example, have to go back here and replacing the last one of here as well. But now the tricky part that people can sometimes do mistakes here. Hopefully I haven't done. So let's see. So what is happening here? So we're going to analyze component by component. So let's start with Fm, right? Because here I have just a sum of them, so we can just pretty much break it in parts, split in parts in this linear combination here of these Fs. So that for Fm, just breaking in parts, right? Just factorizing this. For Fm, what I have, you're gonna see that I can think has an operator, new matrix in the larger systems. That, for example, the first part here for the first component, I'm applying just in the first in the chronometer product. I'm applying this operator in just the first element. So that's gonna be like that. So we apply Fm in the first U component, and the rest is just the identity power of the rest of the elements that is missing there, right? So nothing happening in the other elements. And then, of course, we're gonna do the same for each of the components, right? Until end up with the final part. So nothing happened in the first J minus 1 component, and you apply the last one in the F, right? So that's what's pretty much happening. And when this is happening, actually, you have to look at. So remember that I just removing the element at um here, right? So every time that I'm applying this, actually, I'm applying this in terms of the previous variable that I defined, is this terms of y j plus m minus 1. Because I'm dealing here in the case of j, and then I'm consider m here, but then of course that before was j, so I consider m, so I have to consider the minus 1 that I'm not counting it itself, right? So that's what's happening here. So that's how it's being applied, this the operator. So this I can call this actually, this new guy here has a new operator that we can define different ways, but here's we define it like that: j plus m minus 1, because we're referring that we're applying this for the component j, and that's related with the operator m. And so then the operator m means that you have this application of the nonlinearity m times. And then also remember putting the superscript here, that related the matrix Fn, because in the subscript is related with the new variable that changes, and the component in the the superscript is related with the matrix Fn. And here you're gonna see that this is the dimensionality of it is gonna be the power of this, the j for each n itself, times n m plus j minus 1. So this is the component for Fm. And then for F1 is actually easier in some sense, because F1 I just keep it with exactly the same elements that I have. So look at here. So I just remove the F1 aside, and then you're gonna see that you're gonna keep the same elements of U's that I have at the beginning, I have at the end. So, and then what happens is that you have for F1, you have again the same idea. But then in that case, as I said, you just gonna remove, as I have j components, I'm gonna have to come with I, yj. That's what's happening for F1. And that's in the convention that we're adopting here. I'm gonna call just this by j, because referring the components of y's that gonna be dealing with, and the subscript 1, because I'm dealing with the operator at 1. And this is just in j times nj. This I was dealing with at the beginning the square matrices matrix f1, and here for the new operator is still square matrix. And finally, you have the component of 0 that the f0 actually subtract one element, because f0, you see that doesn't bring any u with it. So that's just gonna remove one. So the operator itself is gonna be, we can call f0 is the same idea. And then here we're gonna deal with one element less, j minus 1, and then you call this a j minus 1, the subscript 0, and that's gonna be element nj times nj minus 1, because now I remove one component rather than added. So at the end of the day, for the component j, for the new, in terms of the new variables, what I'm going to end up with in terms of this new convention of a's, so the more compact way, we're going to have this. And second, go ahead and label the equations, number equations, so that's going to go by 6. And again, this is for, again, I bring in something that was nonlinear in the vectorial case. I bring it now for, again, create a new vectorial case, which is now the new components y that involves these Kronecker products in the compact form. And again, you are couple the system, all the system are coupled with the new components. Now just tweak the max, and you're gonna create again a system of infinite equations, and you have to decide where the truncation gonna be. And again, like just if I wanna write in this compact form without the truncation before, I stop in J, so I started with weight 1 here, and the component of a 0 related go for a vector they're gonna add at the end. I'm gonna show what's gonna happen. So I just hit placing for when I have y here, j equal 1, right? So that's what happened. So I always keep fixed what in the subscript, and then what in the subscript I change according with the value of j. So that's gonna be pretty much these two guys, and remember now this guy here is order m, right? So have like this is gonna be spaced. I'm gonna go for a m component subscript, and then again I shifted by 1 for the next one, but now I included the case of 0, so then I have like now A1, and I'm gonna be shift again for the same amount, and the amount is given, the component itself is gonna be here, what's written, here's 2, here's supposed to be M plus 1. And you keep doing that, right? I'm not gonna write for J here, but it's just the idea, just repeat for J. Here have to be much more pay much more attention for these things. Not be correct because I just had A. I should actually be adding here to be more consistent. Y2 here. Y2 here. And plus the component from V0 that comes from the first component that I couldn't couple with because I don't have Y0, for example. And then I can again do the same procedure of truncation. I do the truncation. And then this matrix is going to be again in the compact form in the AN, IN. And I can write IN like that. This is the case with the F0 is not, it's inhomogeneous case because I have the component of the F0, but here just going to write the matrix AN, which is going to be exactly the same matrix that I wrote before, but now it's limit size. And here actually all these elements here between are 0, okay? It's just to be clear that these are zeros here. And then I'm gonna be like all these elements going through the diagonal, changing the value accordingly with the component that I am. And then I'm gonna end of the day gonna be the final gonna be exactly the truncation. And I'm gonna have one before for the 0. Right? And then I'm gonna end up with again plus some component that you can add that the V0 there. Okay, so question here before I move for the next topic, because I think that's the most challenging. Then the literature, you're gonna see a lot of this already giving, and sometimes it's complicated to understand what is actually this matrix, new components, new matrices are, and the dimensionality they have, all these important things that you have to deal with that to set up your initialize your problem, your D case. Okay, so then I'm gonna move for really quick. The next topic is just I'm gonna mention about the Carleman error. Yes. Okay, this is crucial to develop quantum algorithms. You have to be really good at analyze errors. As I said, like it's really dominant the size of the matrix, and then So here I'm gonna just give it a hint how that things works, because these derivations are quite complicated. But what you do to analyze this, you define a new vector for each component j, right? And this vector that you're gonna define is just you consider the following difference. So what's happening here? So you have these UJs that I wrote is actually the result of the ideal solution. So the ideal solution is the imaginary case that you don't like the truncation. The truncation doesn't happen. So this is the ideal solution for ideal that you consider it in general. And then the yj is actually what you're going to add at the end. So the actual solution. So then there's different strategies to deal with this kind of analysis for in the numerical methods for different equations. Just kind of different approach how we can deal with this error analysis. But here it's important that just to the simplest case, like just to make things simpler, I consider f0 for the solution here. So what you look at how the component itself, each component, you get some bounds for the arrows for each component of your solution. Remember that at the end of the day, you are interested about the final component, because you are interested to extract the first component where the solution lives. And then when you do this analysis, you're gonna end up with the kind of expression that goes like that. There are other dependence here, something like some constants. I mean, some dependence, of course. But the main point here is that usually you see that these conditions that people call by R, and then R should be smaller than 1. So that's the reason, because here is actually you make sure that your problem is stable. That means that your solution not going to blow up. So that's the condition that you needed to make sure that they're going to have a solution that you can realistic. So you don't want that the error blow up. And then that's a condition that smaller the R, you're going to see how much tighter it is, the solution that with the ideal solution. But this is just remember that this is just for the results for the linearization, the linearization. After you have to analyze this problem in terms of the ODE solver that you're going to end up with. So then have to consider, for example, have to analyze the stability condition for the ODE. You're just consider the stability, the error that comes from the Carlemanization. And the dissipation also appear here. So the dissipation means that at the end that like you're gonna have something. You're gonna have like, you can guarantee that you have the initial. So like the idea that you're gonna decrease the equation, how that goes, how the time goes. And this is also another condition that guarantees that you have like a stable solution for the Carlemanization. So this everything appear to have nice and tight bounds. So this is quite important to have this. For of course, this is the condition for f0, but f0 equals 0, but with f1, f0 different than 0, the other condition that I wrote for R at the beginning going to appear. And for different types of ODEs, different conditions going to appear. So this is not coming from like just a hint. It just comes from the numeric analysis, the error analysis. And you're going to see, you have to find out what the conditions that I need to have in order to satisfy the stability of my problem. So that's, as I said, just really quick what I was aiming to talk about this part of the error analysis, because like it demands a lot of computation. Here I'm about 1 hour, so I just try to see if I can talk really quick about the rescaling. So that's gonna be the rescaling, which is quite important. Yeah, so this is important. I think now that you have already watched important lectures here, I think that you already know how to, like, the standard way to encode the solutioning, like in the linear system solvers, quantum linear system solvers is going to be the same here. So for example, the way that like we encode the, for example, AX equal B when you do the quantum version of the quantum linear system solver, how we encode, for example, the vector state B, right? So that's going to be the same idea. So how I encode the solution, how the solution is encoded, right, at the end. So the idea that each amplitude of my solution, so in the ideal case, the vector in the solution of the ODE case, which is not quantum linear case, each component you're going to have a solution that each element you have a vector, if in a vectorial case, and then you're going to have different elements for the vector, right? And then in the vector state of that, in the quantum solution of that, you have the amplitudes associated with the element of the vector that you are trying to extract. So now you have amplitudes uj in the computational basis in terms of j, and j starting from j equal 1. And if I have the vector size of n, as I started before in the classical case, and then you're going to end up with with the logarithmic, the number of the qubits for that is going to be approximately like the logarithm of the dimension of the vector. And this is how you get it, the exponential speed up that you have in the linear system solvers, for example, in this kind of encoding, right? So that's where this exponential speed up in the resources, space resources that you got it for the coding scheme. But now remember that I'm not dealing with this anymore. So I have now a vector where now we have this y's, right? So the solution now is in terms of the y. And then remember that y is now in the truncation is like u, the power of 2 and so on in the ideal case, just to start in the ideal case. And power n, right? So that's what you have actually. So now this is the new vector. So how we encode this? How the solution is encoded? So this is more challenging. So it's just a tensor product of them itself. So the way to represent this, how the solution is encoded in the ideal case, so there's no error. Remember that U is the case that ideal. So I'm gonna just write the compacted way here. So for like a component here M, right? So imagine I have a component M here in the middle, and I'm gonna just write following the encoded that I started here. So in that part here, I'm just doing the tensor product of these guys. And then I'm gonna write, I have J1 until J, each of them going to N, and you have amplitudes associated for each of them. And here's how, in terms of a new computational basis, that you also have to guarantee that's orthogonal itself, because you want to extract the components and then you needed to distinguish between them. And so here, this is like a flag that you needed, a flag that's important for like, for example, you have to flag, for example, to do amplitude amplification. That's quite important to extract the solution. So they have a register for the flag. That's really important. And then you have this basis, like you have like registers associated for each J's related for this encoding, this scheme that I started. So I have G1 for until like Gn, and then I have the remainder of them gonna be just zeros if I have like the size of this n. So then the number of zeros I have like gonna be just for each zeros I have log n, as I said, approximately log n, and then I have the total of register that I'm gonna have here for this final solution gonna be n minus m that are gonna be the one that I have already used. But then you see that now, because we're dealing with the larger system, and you have now we're always doubling the solution, so it's going to be a lot of demanding space, so it's really large. But because I have this logarithmic scheme encoding, at the end of the day, I'm gonna have something that's gonna be dependent linearly n, right? The final register in the computational basis. And this is gonna appear in the complexity of your algorithm. You're gonna see the complexity of algorithm dependent of n. And if you are trying to solve this in the classical computation, classical computer, you're gonna have exponentially dependence in n. So you're gonna blow up. So this is really hard. You cannot deal with this kind of minimalization in general in the quantum computation, in the classical computation. Here we can deal because at the end of the day, it's gonna be linear n because you have this scheme of encoding. Okay, so now just to write in the more compact form to understand how this rescaling works, I'm gonna write in the compact form this element of the basis. So I just have the subscript for n to relate with the indices that I am, J1, related with how many, which component J I am, the component M that I am in that case. So that's the way that you write this in the more compact form. You can, if you have other ideas for how to write this, you can write this is something not like established. Okay, so what would end up in the end? So we're gonna enter the solution of your ODE after linearization. That's how we're gonna write the solution. This is the linear combination that I'm gonna end up with for J equal 1. And then I'll go for J1, J2, and so on until the component n, capital N. Okay. Okay, now we're gonna understand why is quite relevant to do the rescaling of this. So now we have to make sure that normalization happen of this state, right? We have to deal with the quantum state. The quantum state has to be normalized. So we have to guarantee that this is true. And then I can write has the normalization, like everything gonna be normalized in terms of, I'm gonna call by this by the normalization factor gonna be this 1 over square root of Vn. And what is Vn is? Vn is just the norm of the vector that I start with, right? This vector here. So then if you compute the norm of this, following this product, tensor products for this, like this, how I said, like the copies, the multiple copies that you have to consider in the solution. That's what I have to deal with. And here I'm assuming that for this calculation that ut, the norm of ut of the initial vector that you start is larger than 1. And then I'm gonna end up with this expression easy to compute. And then if remember that at the end of the day, I'm interested about that component. So I have to amplify that component. So that's where I want to see what is the probability of success to extract that component. So I have to flag on that. That's the reason I have the flag registered. So then if I look at after the normalization, the probability of success to measure the component that I'm interested is another calculation that's not difficult to do it. Oops. Okay, then I project on that guy. I'm gonna just use the normalization that I have considered already. So this has to be considered now in the equation 2.5. And then I'm gonna end up with the expression with the results of in terms of these norms. And that's tell us already essentially why that's going to be exponential dependence in n in the so the order of normalization. So the idea that in general, so if you don't have the rescaling that I'm going to talk, you want to increase the dimension of n because you want to have a higher precision of your Carleman solver of the linearization. But by increasing that, also you're going to end up by decreasing the probability of success. You don't want to, so you want to do that, but you have to be like always looking for a trade-off because you know that you have to do amplitude application on that, and amplitude application, the order of application that you do it is in terms of the inverse of the probability of IT, right? Square root of that. So then you're going to see previous results that the complex of the algorithm of the quantum solvers in terms of Carlemanization are going to have like something like dependent in terms of U in exponentially in the capital in the order of the Carlemanization. And that can be good, can be not expensively dependent of the initial condition that we're dealing with, assuming that we're also dealing with dissipation. So that U in actually is the highest value that you have, that you start with. So that's the reason that uses for the bounds. And the linearization, like the rescaling is quite simple. Like, so the idea of the rescaling that from the case that I have F0 again, just make simpler. You just rewrite this tilde here. That means that I have already the rescaling. So I have to do consistently do rescaling all the components. And then I'm gonna see that if in that case, if you can do dimensional analysis, you're gonna see the F1 actually is the same, keep it the same. Fm is gonna be what I call by this rescaling by gamma, and then I'm gonna tell you what gamma is. And tilde itself is. And so you can guarantee that if, again, remember that we're dealing with dissipation, if gamma is bigger, larger, or equal to UN, you can guarantee that you're going to end up with the probability of success to measure the component that you're dealing after the rescaling. You're going to be larger or equal. If you want to go larger than UN, you're going to be larger than 1 over n. And now the rounds of amplitude application are going to be pretty much the square root of n. Going to be rounds of amplitude amplification. Okay, so like I think I finished now because more than 1 hour. I mean, I would like to keep talking about it. Like now that you have this, because I was planning to talk after that one about the nonlinear diffuse equation. So how actually you map this PDE to the ODE, and then I have another issues that with this. And then I was planning to talk also how the discretization works, and high order discretization works as well, which is important for this problem. But I'm afraid that I don't have time because more than 1 hour, so I imagine that people are tired now.
Pedro, so yeah, we don't have any other session planned after yours. So if you want to take 15 more minutes to wrap it up, yeah, you're welcome to.
Okay, so like maybe people can tell me also if they actually want to see this, how that works, or yeah, if we get some feedback that how people are feeling, they wanna that I continue a little bit more or not. So it's up to the audience.
Yeah, okay. I'm gonna wait a few minutes on Discord. Let's see what people are saying. Yes, please keep going. Yeah, I think what can be like really good would be to kind of give like a high level intuition on like, how this technique can be used in practice. I think that can really nicely wrap it up.
Yeah, okay. So I mean, this is actually, of course, because the ODE that I just wrote is something like, it's too much, like you cannot see any practical problem for that, like from the first instance. If I just look at it, like, oh, what I'm trying to solve there. And this is the case that you see a clear application.
Mm-hmm.
And that's, again, this is the case that we start with a scalar nonlinear PDE. So the function is scalar, and that dependence is a vectorial dependence, like it's like it is. So we have ut, u is a scalar, but then you have the components are a vector in a space, can be d-dimensional as you want, and that's gonna be here the Laplacian, the operator, plus some component here, linear u, and then you add the nonlinearity, the power. And then here, remember, just a scalar at the first moment. Okay, so then I just have to be really brief about how the spatial discretization works. So for who doesn't have actually knowledge about it. So here really quick. So here just dealing with this finite difference method, spatial discretization. So the idea is to how I can approximate it. I'm always gonna break this in like each element of my function that is like continuous function is some domain that we're gonna determine. But then since I'm doing some numerical methods, I'm gonna just have like you decide how many points that you have to use in that domain that you're gonna use. And for each of these points, you're gonna assign, the value of the function that initialized for that particular point in time. And then you have to deal how you're gonna deal with this like derivatives, approximation of the derivatives, and etc. So that's how that comes from the methods for discretization, how we approximate it is really important to the techniques for the approximation of the operators. So usually like there's an example, like I have some second order derivative, and the idea that I can approximate it for this D2 here that I'm calling this is approximation. The idea that you have like you want to try to approximate the second derivative. This is just a simple case how that works. This is the case that I have one dimension in space, for example, or actually would be larger dimension in space. But this is just consider the one dimension X. And then there are different methods that we can approximate this guy with different order of accuracy of this guy. For example, here just going to show the first order of approximation, that the order actually is in squared h. What that means h here is that you have this function u, there's a class C3 of function in that specific domain that we're trying to expand here. and the domain involves that the region from H for a central point X bar to 2 plus H, and the C cube means that the function is continuous and the derivatives of this function is also continuous into the third order derivative. And this function also, assumption that the function also has a fourth derivative, but it's not continuous. So then you can like show like different ways to do that, but easier way to do that, you can approximate by show the methods of approximation of this using the Taylor series, for example. For example, you can show that this kind of approximation here, uxt, so you can show that this operator is gonna guarantee this order of accuracy. And then the way to do that, like you see that how I'm coupling the elements of the neighborhood by the displacement for H. So you have this domain space that is discretized, and each element is gonna be the neighbor of that for a single point. For example, this could be like I plus 1 for starting from a point the center I, and this is gonna be I minus 1. You can do to show that this actually give this order of accuracy in the approximation of the derivative, second derivative. You can just do the Taylor expansion of from the after the shift of by H, starting for the J plus H. You also do the Taylor expansion, consider minus H, and you add all together here. And then you're gonna see actually gonna have some approximation for the second derivative and the approximated order H squared. And then also there's another way to write this in terms of like the Laplacian operator. So this is actually could be rewritten like minus 1 over H squared L, and L people call it by the Laplacian operator, and it can be called by D square. And then what end of the day, so like I have like H squared gonna be, as I said, in terms of these grid points that I define. So the values of the function that I know just the values of functions in specific given points in the grid points, and I can use it then to define operators. And then, for example, for a uniform grid, we can sign the elements like this, H, and then H itself gonna be like any plus 1. So that's this displacement, how the displacement between one element to another element that you have. And then this is really nice because then we can write this as an operator, as a matrix form. This is going to be pretty much 1 over H squared. Like consider the periodic boundary condition for this Laplacian, and we're going to see that you're going to see that that is missing actually the factor of 2 here, if I don't remember well. I think there's a factor of 2 here. Yes. So you're going to see, it's checking. So you're going to see this Laplacian given by this operator. And so on. Applying from in the grid points was 0 to n minus 1. Okay, that's a mess here, but just to have an idea how that discretization works and how this can be turned in a matrix application, matrix operations. And then, as I said here, the initial problem that I have, and then you're going to apply this method of the discretization, and it's a bit more sophisticated than that, but you can show, once you discretize, you can write the matrix F1, that I remember that I have like F1 and F0. I can write in terms of the Laplacian operator, so I can rewrite that in a compact form, LKD plus C identity. So here what I'm going to have here, so D means that I have D dimensions. So the Laplacian operator that I just wrote in the top here is the Laplacian for a single one direction. So when I have D here, I actually have the easiest way to write in D direction. So like for each X, Y, and Z components. And K that I wrote here means the order of the Laplacian operator. So K is related with this approximation H here squared that I wrote here. So the K is going to be pretty much related with this, the power of the approximation here. So then you can show, once you discretize, you're going to end up with F1 you can rewrite in terms of the matrix, in terms of the Laplacian, you see. And then Fm is in terms of, once you discretize this nonlinear part here, you're going to end up with the terms of the tensor, the Kronecker product of Um. And then Fm is related with this part here. So it's going to be pretty much related with this component and then the factor B here. But that's how that's relation or how they create Fm is not exactly this, because it actually is a matrix expression for that. But the matrix comes, the Fm gonna come from the result of the discretization of this operator, this component nonlinear of the non-diffusion equation. And then to have idea how this Laplacian is expressed, like for the order k, there's a nice compact way to do it. It's like n2 power d, where n is the number of grid points for each direction. So d is the number of dimension. And then it's a compact way to write this. Where S is the circulant matrix. And as we increase the order, so we're going to be, for higher order Laplacians, we'll have just to increase the sum of the k here. And we're going to have a larger order of the approximation of the Laplacian. So it's really easy to write. This is for the periodic boundary condition. And this is like how we write the components of the circulant matrix is quite simple, like in terms of the Kronecker delta, like J plus 1 is pretty much just a shifted of the diagonal. So for example, for the K1, which is the case that I wrote here, you have like this comes from the -1 comes from here, this part here. So you have the -1 in both sides, and from Zj, Sj minus 1, and the identity gonna come A0 here, come from the diagonal part. It just come from like, you can just find the right component element for A0. And then there are actually methods to find which gonna be the A's and AJ, A is in general, right? There are actually methods to find out this. So the problem that once you have done that, so then you're gonna end up, so you do the spatial discretization, you're gonna end up with the ODE, and the ODE gonna have exactly the same form that I had in the beginning. So now I have the structure of F1. I have another F1, Fm, which is not exactly this, I didn't wrote here, but there's a closed form for Fm too. And then we'll go back to apply the same methodology to the linearization. You apply everything that I showed before. But here you have to be careful adaptation of the stability condition. This is just I want to call attention here for R, because remember how we define R, which is Fm here, U in, and -1. Which for us in the case that we're dealing with, you can show actually that the norm of M is equal to B, and here the maximum eigenvalue here of I0 is gonna be pretty much, it's gonna be C. can prove that for that particular case that we show. And then we're gonna pretty much end up with P over C U in. But the problem comes from this part here, because once you do the spatial discretization, if you consider, for example, the two norm, you're gonna see the two norm increase has to increase the discretization points. Because the idea here is like the Laplacian operator. So there are two ways to actually increase the accuracy of the operation of your solution or your method. You can pretty much increase the number of grid points. Remember that the grid points at the end of the day gonna give smaller values for h, so you have more accurate results for your approximation. But with the trade-off, you have to deal with the larger systems to deal with, right? So I have a larger difference equation to solve, larger system for difference equations to solve, better accuracy. Another way to do it is to increase the order of your Laplacian. So your Laplacian can be increased by the order k here, with a fixed number of grid points. So what happens is that you can increase the accuracy as well, but with the downside that you're gonna decrease the sparsity, right? So you're gonna have less non-zero points here. So you're gonna have a stencil with more points if you go for like larger approximations, higher approximations in terms of the Laplacian for a fixed number of grid points. So I also have the question about your complexity of the algorithm, how are the dependence of each of the parameters. So for example, for the sparsity in general, the dependence of the linear solvers are the quantum linear for P's in general is linear in S, the sparsity. But then you have to see how going to be the dependence in terms of the dimension of the problem, because I also have a really bad dependence in terms of the Carleman linearization that comes with the order of n as well. So then I have always to look at the trade-off between that. And the problem of this R condition, the stability that, as I said, has increase the grid points to increase the accuracy, you're gonna increase the value of R, so you might not get a stable solution anymore once you do the linearization. So one way to there's a few ways to not avoid, but to decrease this consequence, right? If you wanna actually find a way to avoid this problematic with the stability condition, you can find the stability condition in terms of different norms. So we can show that the solution is not going to blow up in terms of different norm conditions. And one norm condition can do that in terms of the max norm. And the max norm of a vector doesn't depend on the number of discretization points anymore. So that's the one way to analyze the problem in an alternative way. Another way is you can control the number of grid points. You can find like a really ratio between B and C of your problem. And then you can control the number of grid points that you have by increasing the order of the Laplacian, right? Without increase the grid points, as I said. And then you can keep the problem with good accuracy. So that's the way there are actually more things should be analyzed that don't have time, because also have the condition of stability condition to solve the ODE problem that you have to deal with. Is a different thing that you have to analyze, different analysis that I have to do to make sure that your problem is not gonna blow up in the solution of the ODE solver. But this is the starting point. So the starting point for the nonlinear ODE, that is actually in that case the nonlinear PDE that I have discretized, and then because of the discretization, I can get it, even if I start with a problem that is stable before the discretization. Once I do the discretization, I can end up with something not stable anymore because of these conditions of the Carlemanization. So then I have to be careful. So I have to be careful in terms of how many grid points I have to use, what the order of the Laplacian, the approximation of the operators that I have to do, or do different types of analysis for different types of norms, analysis for the error. So all of these things have to be carefully analyzed to see if you have an efficient algorithm at the end. So I think now I finished that part that I was aiming to go.
Yeah, that was great. Thank you so much, Pedro. Maybe we can kind of wrap up with like one kind of high level question, maybe. So, what are like the pros and cons of the Carleman linearization approach? In what cases can you effectively use this technique to handle nonlinearity? Maybe what are your thoughts on that?
Well, I mean, this is like in the quantum computation, like in classical computation, I don't see this as a feasible way to do it. And the reason is clear because as we do the linearization, the system that we're gonna end up with, the ODE system, is gonna blow up in terms of the Carleman order. And then if you wanna have a higher accuracy, you need a higher order of the Carleman. So they have a larger system for the truncation. And this is like, I haven't talked about the Navier-Stokes, for example. The Navier-Stokes, you're gonna see that, for example, when I have nonlinearities in terms of imagine that I have nonlinearities in terms of the partial derivative of the function that happens in the Navier-Stokes, for example. When you do the discretization of this and then map it for the ODE case, you're gonna see that R is gonna be pretty much dependent in the number of discretization points that you did it. You're gonna be pretty much dependent in the or in n. It's gonna be something like proportional to the order n. And then you cannot handle, in general, in terms of finite difference methods, you cannot handle for this kind of nonlinearity in the derivative of the function because you're not gonna guarantee any stable solution. And the reason that we believe that they're gonna be handled in general for like if you can make sure that this method is gonna work, you can have a stable solution. So the question is, why should I go for the quantum solver or not so quantum solver? So then you go back to the same question of the ODE solvers, like, should I solve PDEs, ODEs in the quantum computer or not? So this is the question that we still don't know actually how much better it's gonna be or not. But the hope is that because like that the quantum solvers will have in general like now the best the best quantum algorithms will have like cap log 1 over epsilon, and then also have, which is pretty much here, comes from the block encoding, etc. You have like log n, which is the dimension of the matrix that we're dealing with, like the dimension of the problem that the vector that is dealing with. So the vector size n, you go log n. But then the question here is like, when actually gonna be good for me to solve that? Because you have classical solvers. So let me try to go. I'm gonna go back for the ODE. So you have a classical solvers that gives like the conjugate gradient, for example, like have the complexity kappa, the square root of kappa, the same in the arrow, but it's linear in n. But then, okay, so you can see, oh, I have like exponential speed up here in n. But what happens in practice that for general problems, you have the condition number proportional with the dimension of the matrix that we're dealing with. So then we lost, like in practice, we do not have any exponential speed up. And also in general cases, like again, the solvers, the quantum solvers are dealing with, we have to deal with some global property because you cannot extract it, all the components of the vector at the end of the solution. Otherwise, you're gonna lose the exponential speed up in the coding that you have for the log n. So you lose that. So then in practice, you'll have to be dealing with that. So the condition number, if you have the condition number being like proportional with the dimension of the system, the matrix that are the linear system that are trying to solve, you already don't have any exponential speed up. You have like a factor exponential polynomial increase again, like speed up. But why do you have the hope for ODEs? The hope for the ODEs is because the condition number for the ODEs in general case for this, when you have the discretization of these matrices. So what happened is that in general, the dimension for a d-dimensional problem, right, increase like n power of d, right? So that's going to be pretty much the dimension of the problem that we're dealing with, the linear system problems, independent of the dimension. So then when you go for the quantum solvers, this goes for a dependence linear in D, right? So then you have like now a complexity is going to be like D kappa log 1 over epsilon log n. And then you are against now something that the classical going to be power D, right? Like take the conjugate gradient, you have now power D. But so the question is about kappa. So how kappa goes? So the kappa, in most of the cases for the ODEs, kappa doesn't depend on the dimension. So the gain is the dimension. So then you're gonna have like the speed up is pretty much gonna be in terms of the larger dimension problems. So like in the practical cases, people are gonna deal like I think in like 3-dimensional case. So they're not gonna be something cubic, and that's gonna hope for. But if you find something multidimensional, better. But that's what I aim for. And then for the nonlinear linear PDEs or these, it's gonna be the same thing. The same thing gonna be appearing. You are hoping for these speed ups there. And the question is about the order dependence of the Carleman now they have now the complexity gonna appear also the dependence of n. So the question is how now the dependence of n is gonna be compared with the other classical solvers, like we have to do like solve a system of nonlinear PDEs, different linear equations. So then you have to analyze how the complexity is gonna be compared with appearances of this n here that in the complexity. But of course, for large dimensions, you still don't have the exponential dependence in D. It's gonna be linear in D. And so the question is, you're gonna be good or not? I still like, from my understanding, it's an open problem. And then also you have to find out exactly like this complexity analysis asymptotically. You have to go back and also like do the proper resource estimations. You see actually the speed ups that are gonna have actually it's gonna be indeed gonna appear in the total time when you have to do in the practical cases, right? So yeah, so there's some open questions. The hope is that in that terms of this the dimensionality, and also because the other hope is that you're gonna be dealing with, in principle, with less resources. You can do it with larger and larger dimensionalities that possibly we cannot deal with in the classical computation. So maybe if you are regimes that people are interested that larger that you can handle at the moment with the classical computation, that's where the quantum computation can be good for. So that's pretty much that.
Yeah, okay. Thank you for that detailed explanation. Once again, thank you so much, Pedro, for taking the time to come and talk in our program. I know it's super late for you, and I really, really appreciate you taking the time to do this. So thank you again.